Homework pressure? No more. At Spring Library, we explain every topic in simple way. Join the learning family and score high every day.
So for the first part, we use equation 27.5p to calculate the maximum kinetic energy. So according to this equation, the maximum kinetic energy is equal to h times the frequency minus the work function. And this we can set equal to the product of the electron charge times the stopping potential or the stopping voltage. Now we know that this frequency is given by the speed of light over the wavelength. So we have hc over lambda minus the work function equal to E times the stopping voltage. So we use this equation to solve for the stopping potential, which is then equal to hc over lambda minus w naught over the charge of electron. Now solving this, we get, so the value of hc in electron volt is 1240 electron volt times nanometer, and this has been calculated in previous problems. So if you want, you can look it up. Over the wavelength, which is 464 nanometer, minus the work function, which is given to be 2.28 electron volt, over the charge of electron. So let's call this E because we have electron volt here, so E will just cancel out directly. So V naught will be then, so E just cancel out from each of them, and then we get the potential to be 0.3924 volt, or nearly equal to 0.39 volts. So this is the value of the stopping voltage. Now for part B, we calculate the speed from the non-relativistic kinetic energy equation, which is k equals to half mv square, and we use the maximum kinetic energy. So Vmax will then be equal to 2k Emax over m and the root over of that. And so we have the kinetic energy, which is E times the stopping potential. So this will just be 0. So this will just be 0.3924 electron volt, because we have volts here, and multiplying the charge of electron will just make it electron volt. So this times, so we have to convert this energy into joules to find the velocity. So we multiply a factor, we multiply this over, we need the mass of the electron, and then we take the root over of the whole thing, and we get this velocity to be 3.713 times 10 to the power 5 meter per second, or you can say approximately 3.7 times 10 to the power 5 meter per second. Now comparing it with the velocity, with the speed of light, we see that this is nearly equal to 0.001 times the speed of light, which is very less than the speed of light. So we are justified in using the classical definition of kinetic energy over here. So this is the value of velocity that we need. Now, for the last part, to calculate the de Broglie wavelength, we use equation 27.8. According to this equation, the wavelength is equal to Planck constant over the momentum. Now, since we have already justified our use of the classical definition of the energy, we can use the same for momentum. So classically, momentum is m times the velocity. So this is equal to the Planck constant, which is 6.63 times 10 to the power minus 34 joules times second over 9.11 times 10 to the power minus 31 kg, which is the mass of the electron. And we use the value of velocity here that we calculated. So, and we then solve it and we get this value of wavelength to be 1.96 times 10 to the power 9 meter, or nearly equal to 2 nanometer.